So this video is another example of using partial fraction expansion to find the inverse Laplace transform of a function that we can't find using the basic table of transforms that we're given. And this is going to be another application of the partial fraction expansion, but it's going to be different. A partial fraction expansion, there's much more to it than what we used in that previous example, and we'll see that up here, where we just simply wrote, this whole term 2 over s minus 2 times s minus 3 times s minus 6 as a sum of these, arbitrary constants over the factors of the denominator. So we'll see a little bit of a difference in the way we approach this problem. First of all, we see that our inverse Laplace is, we're given to find as 1 over s cubed plus 6s. And the good thing to always do with partial fraction expansion is to create as many factors as you can on the denominator and on the numerator as well. But typically we'll have the denominator having, the most factors. So what I mean by that is if we have like s cubed plus 6s, we're going to want to factor out s here and s squared plus 6 here. This is perfectly equivalent to s cubed plus 6s, but it's going to help us with partial fraction expansion. And that's what the essence of partial fraction expansion is. We want each individual factor here so that we can write our equivalent fractions. All right, so basically, and that's step one. In step two, we want to set, notice how we set 1 over s times s squared plus 6 equal to a over s plus bs plus c over s squared. Now, this, using following the example that we did before, this should just be, b over s squared plus 6, right? A over s plus b over s squared plus 6. We just put a constant over each factor. But in fact, it depends on the nature of the factor. So if we look at s squared plus 6, we actually have to make sure that this factor has real roots. If it has imaginary roots, we're actually going to write a term bs plus c. bs plus c. And the reason being, if we look for the s, for example, if we want to find the roots of s squared plus 6, we'll set that equal to 0, right? In using the quadratic formula, we will find that we're going to have imaginary roots. And so that's why we write bs plus c over s squared plus 6. And this could be, if it was, a bigger term, if it was, s cubed plus, some other terms equal to 0, and we have imaginary roots, we actually do a similar thing where we actually do, for example, bs squared plus cs plus d. So it kind of has a form of this, basic polynomial where we're just adding, more and more terms. But in this case, we have s squared plus 6. So the highest order here is 2. So that's why we're going to have on the top here, the highest order on the top is going to be 1. So we're going to have bs plus c. So that's a good thing to remember. So basically, to recap step 2, we just want to make sure that this term, if it has imaginary roots, we cannot write just b over s squared plus 6. We have to write that bs plus c. And this is just a rule of the partial fraction expansion here. All right. So our work becomes to find a, b, and c in the same way that we found in that first example, right? In this case, we have, let's see, s equals 0, So we set s equal to 0, and we cancel out this entire term here. And it makes it easy to solve for a, so we found a. And then we can't, because of the fact, and you'll notice, because there's no way to get rid of this term here completely, right? We're going to have to consider a here, and there's no way to isolate b and c to solve for one independently. So we actually have to create two different equations. It's not like where we were able to cross out an entire term because that term is equal to 0. So we actually arbitrarily choose s values. We can choose any values for s based on how many unknowns we have. So we have, we're looking for b, and we're looking for c. There's two unknowns, so we're going to need two different equations. So we want to let s equal, let's say 1 here. We could do 4, we could do 10, we could do 100. I chose 1 because it's a small number and it's easy to work with. And we do a couple of, substitutions here, simplifications, and we get 1 equals 7 over 6 plus b plus c. That's our first equation. Our second equation is just choose another s value. I choose s minus equals 2 because that's an easy small value to work with. You plug in everything and you end up with this second equation, negative 2 over 3 is equal to 4b plus 2c. And this basically just turns into some algebra, right? You have two equations, you have two unknowns. You can use one equation to plug into another. I chose equation 1 and I put it into equation 2. And we end up here, after a couple of lines of work, we end up with b is equal to negative 1 over 6. And we'll kind of talk about this here, right? We have, first of all, we use equation 1 to solve for c. So we have that c is equal to negative b minus 1 over 6. And we use the fact that c is equal to negative b minus 1 over 6 and plug that into equation 2. Equation 2 becomes an equation strictly of b's here, and that's why we're able to solve for b. And using any of the equations, we use 1 here in step 5, and we find that c is actually just 0, which is convenient because we have a simpler problem. All right, so now that we've solved for a, b, and c, we can rewrite our problem 1 over s cubed plus 6s as basically this form here, but we already know our a, b's, and c's. So we're going to plug in 1 over 6 for a. The b that we found is negative 1 over 6, so that's why we have this minus here. And the c is 0, so this is really plus 0, but we can just leave it alone there. And now we have something that looks familiar that we can use a table of transforms, right? We have the inverse Laplace transform of 1 over s. So we've pulled out here, we've pulled out the 1 over 6 because it's a constant. And that simply just turns into 1. And so we have 1 over 6 here in this answer here. And the inverse Laplace of, well, s over s squared plus 6 here, because we've pulled out the 1 over 6. Using the cosine inverse transform, we know that we have s over s squared plus k squared. In our case, 6 is equal to k squared, so k is the square root of 6. And we do the substitution, and we find that we end up with cosine of the square root of 6 times t. And putting it all together, we have 1 over 6 minus 1 over 6 times the cosine of the square root of 6 times t. So it's important to basically remember that their partial fraction expansion is going to look different in certain, I went too far here, in certain problems. In the problem where we have nothing but real factors, which is this problem here, we have, right, s minus 2, s minus 3, s minus 6. The roots of these are 2, 3, and 6, right, respectively. Because if you plug in s is equal to 2, this is a 0. That's a root of s minus 2. If you plug in 3 here, s minus 3, that's a root of s minus 3. If you plug in 6 here, that's a root of s minus 6. and that's a real root, right? 2, 3, and 6 are real numbers. If we do try to do the same thing here in this problem, right, s is equal to 0, that's a root of s, but there's no real roots of s squared plus 6 equals 0, because if we try to solve that, we get s squared equals the square root of -6, and we end up with imaginary values of s. And so that's why we slightly have to modify our form here, right? Where we do bs plus c, and it can define this a little bit more rigorously, or just practice these. And there's not a lot of variation in the problems we'll see, where we'll typically get maybe one factor that has imaginary roots, and we just have to make sure that we write bs plus c, and so on.